thanks for coming to the May edition of Papers We Love.
Yeah!
You've all heard about the pizza. Sorry about that. Other things in other news, there's another thing I've been bad at organizing. If I promised anybody else here in this room, or if you know anybody who has talked to me about possibly speaking at a future meetup, can you get them to message me again? I might or might not have lost the emails. Anyway, yes, I do.
Okay.
Yes. Anyway, today we have Paul. He's going to be talking to us about CRDTs and probably telling us what the C means.
Yes. Thank you very much. So first of all, thank you to David and James for organizing. Thanks to Shopify for hosting. Like David said, I am going to talk about CRDTs today. And like he hinted at, the C is often ambiguous. So the inside joke there is, how many people have actually read the paper? Don't be shy, it's okay if you didn't. Okay, so like a few. How many people have never heard of CRDTs before the context of this talk? Okay, cool. So the CRDTs stand for either commutative replicated data types, or conflict-free replicated data types, or convergent replicated data types, and they're all slightly different. I am not going to go into the differences between those three types of CRDTs. I'm just going to explain the general concept, and we can have an interesting discussion about the differences if you're interested, but it's not really core to the understanding. So very briefly, CRDTs are data types whose operations commute when they're concurrent. That's the general idea. So the replicas of a data set will converge without any sort of central consensus. And I'm going to go into definitions of all those things if those are new terms for you, don't worry. Obvious disclaimer, I'm not an expert on CRDTs. I'm not an academic. I find this stuff really interesting, and there's a whole body of work here. I'm not familiar with it at all, with all of it, but I find it interesting, and hopefully you do too. So the paper that I'm actually talking about is called CRDTs, Consistency Without Concurrency Control. And it was published by a group of people. The lead author was Marc Shapiro, who works for INRIA. And it was published in 2009. It's not the first paper that talks about CRDTs, but it's kind of considered the seminal work on them because it walks through implementing what they describe as a non-trivial example of what a CRDT is. And so it's interesting for that reason. There's been a whole bunch of work done since this paper that addresses some of the ambiguities, some of the challenges that are observed in this paper. And it's important to note, you'll get the sense as I'm walking through this, that it's a very exploratory paper. It's kind of looking at, we have this concept that seems mathematically sound. What happens when we move it beyond, the theoretical and try to implement something that's non-trivial and can solve a real-world problem? So CRDTs have to do with distributed systems. They're attempting to solve a problem that's pretty fundamental to distributed systems. So let's start with looking at what a distributed system is. Wikipedia has a pretty simple definition. It's a distributed system is a software system in which components located on networked computers communicate and coordinate their actions by passing messages. That makes sense to everyone? You got networked computers. And I'm going to rip off a quote from a friend of mine and former colleague. They're also generally a bad idea, best avoided. So, the point here is distributed systems are hard. It's hard to get a group of computers to agree on a state of reality. And, the reasons for that are well known and also not known. There's a whole host of reasons. There's a great little article out there, I guess you could call it an article, called The Fallacies of Distributed Systems. And it's just a list of, things that you can take for granted if you're creating just models of problems. And they're things like, the network is not reliable. That's it's a fallacy to think that the network is reliable and that messages won't be duplicated, dropped, reordered. The idea that networks actually work 100% of the time the way that we expect them to is a fallacy. So if you've done any sort of reading about distributed systems, or if you've worked with distributed systems, you may have come across this idea of the CAP theorem, or otherwise known as the CAP impossibility result. It's also sometimes called Brewer's conjecture, named after Eric Brewer, who observed that, given the following properties, consistency, meaning all replicas of a distributed system have the same view of the world. Availability, every request to a non-failing node in a system will generate a successful response. And partition tolerance, meaning the system continues to operate despite arbitrary message loss or failure of a part of the system. So if nodes can temporarily not communicate, they'll diverge, but they can eventually converge on some sort of state of reality. That's partition tolerance. The idea behind the CAP theorem is that you can't have all three, you can have two. So in this Venn diagram, you have consistency and availability, or consistency and partition tolerance, or AP systems, but you can't have all three at once. The trouble with the way that we talk about this a lot of the times is that it's really an oversimplification when talking about real-world scenarios, because you can't really choose whether or not your system will experience partitions. So a partition being, like I said, a state where you have a distributed system and nodes in your distributed system temporarily are unable to talk to each other. That's, your system is partitioned. The realities of networks and switch failures and all sorts of things mean that your system is either going to have to experience partitions or it's not going to experience partitions. If it's going to, when we're talking about distributed data stores and things like that exist on networks, they're going to experience partitions. And so that means that you can't have strong consistency and availability at the same time. You have to figure out what trade-off you're willing to accept. And so in the real world, you have systems, AP systems and CP systems. You have some systems that claim to be CA. People claim they're a lie. Oftentimes they are. Really, it's, an example of an AP system is like Cassandra. Cassandra with certain configuration tunings will, lean on the CA side, or sorry, on the CP system, AP system. I'm confusing that. CP systems are like Zookeeper, etc.D that favor, strong consistency and partition tolerance, but not necessarily availability. So when we're talking about this and why it's a problem, let's look at what a distributed system is. So let's say here we have a client and we have a single machine, some single server, and the client just wants to read the value of some variable. So in this case, the client, the red dot, is asking the server, what's the value of X? And the server says 8. This is a read-only system, right? There's only one operation happening here. It's asking for the value of something and it's getting a value back. This is really easy to scale, right? So if you wanted to scale this out and make it available, highly available, you just add more replicas of the data that you're trying to interrogate. So in this case, the client can ask any node, any replica, what's the value of X? And because there's no write operations, there's no mutability in this system, you're going to get a consistent view of the world just because. So it's really easy to scale. Writing is where things get tricky and where the CAP theorem becomes interesting. So in this case, a client's writing to a single replica, okay? So it's writing to a single node in a cluster, and it's setting the value of X equals to 10, and the node gives back some kind of response saying that it accepted the write. So it's saying, okay. Right, so we can now reliably say that as far as that node's view of the world, X is equal to 10. So if the client goes back and tries to get that value, if it talks to that node in the system, that's going to be fine. The node said I accepted the write, X is now 10. If I ask what the value of X is, it's going to say 10. But if the client tries to read from another replica in the cluster, it's going to get a different value because before we had a read-only system, we wrote to one replica, sorry. There was no way to replicate those changes to the other nodes in the system. So you need a way to migrate the changes to other replicas, and this usually involves some kind of replication strategy. So replication strategies can be either state-based or transaction-based, but the point is you, as the client, write to a single primary in a system, and you set a value of X equals to 8. That primary does replication, and there's a different group of different techniques that have different pros and cons. But then it says, okay, every node in the system now knows that X equals 8 in this case. So you're guaranteeing consistency here. What you end up seeing in the real world is this is a lot like how MySQL or PostgreSQL will operate in a single primary system. So in a setup like this, you write to a single primary, and that's it. In other words, it's not very available. So we're sacrificing availability here. Now, looking at a multi-primary setup, this is where things get really interesting. So in the previous example, a node can talk to a single primary in a cluster. For writes, it can read from any of the secondaries and it will get a value because it's been replicated out to those secondaries. But that's, again, not very available. If we want to make sure that you can send writes to any member of a system, any replica in a system, then you end up having to deal with conflicts. So in this situation, you have a multi-primary setup, and you have two clients that are concurrently talking to two different nodes in a system. One is saying x is equal to 8, and it gets an OK. One is saying x equals to 10, it gets an OK. What is the actual state of the world as the whole system sees it? So now if you go to ask any other node in the system, like what's the value of x, you have no idea what, without knowing how this system is going to resolve conflicts, you have no way of knowing what the value of x is going to be. So this is an unideal situation. So this is what we call a conflict, and the typical way to resolve conflict is to introduce some kind of system that guarantees consensus, okay? So you have different replicas in a system. It's going to guarantee, you're going to have some kind of protocol where all of the replicas in a system will converge on a state, saying x is either equal to 8 or x is either equal to 10. Which write did it accept? There will be convergence based on consensus. So things you need to do in a system like this is, oftentimes some systems require that there's one primary or like one replica that's designated as a primary. So you'll need to do some kind of leader election every once in a while. That's fine. So consensus systems can allow you to do leader election. But then the more common thing is a write committed to the whole system? So have we all accepted this write? Is this the state of the world? You need some protocol or some mechanism for all of the systems in your cluster to agree on that. And that's typically called a consensus protocol. Some of the examples, they're a bit out of scope for this paper, but examples for people who are interested are like Raft is a fairly recent, sometimes called a hipster consensus protocol because it's new and it's cool and everybody talks about it. Zookeeper uses something called ZAB, which is the Zookeeper Atomic Broadcast Protocol, if I'm not mistaken. It's based on an older protocol called Paxos that was pioneered by a guy named Leo Lamport, who's done just a ton of stuff in this space. Or sorry, did I get that name wrong? Leslie Lamport. I always do that, actually. All right. So the tricky part about consensus is that consensus can be slow. It's fault tolerant. So in other words, in a system where you have different replicas, typically if you have some kind of consensus protocol, you can tolerate at most a loss of half your cluster. So you need to have half plus 1 usually to have some kind of quorum about what's happening. So it is fault tolerant, but it's also really slow. And there's a lot of research that goes into showing that this is a bottleneck in a distributed system. The way I like to think about it is in order to guarantee some kind of strong consistency, every node in your system has to think about a total order of updates to converge on a certain reality. Right? So if you have a total order of updates, it needs to know, okay, apply this, and then apply this, and then apply this. What this means is at some point, you probably have a counter in your system. And so every node has to agree on what value that counter is at for each operation, which means that you've turned a massively parallel system into a sequential system, which means you're going to run into scaling problems with this. And this is why in the real world I mentioned Cassandra as an example of an AP system, but it has configurations where you can sort of dial it in one direction or another. And that's usually what ends up happening with a lot of data stores that we end up using. So one solution to this problem is eventual consistency. The idea that you can write to a replica in a system, and eventually all of the nodes in your system will converge on a state. It won't happen immediately, so this is different than strong consistency, where if I write to something, I should be able to ask for that value from any other node in the system and just get that value back. This is an acceptance that for a certain period of time, the state of reality will diverge in your system. You'll have different meanings of what the state actually is, but eventually they'll converge on one version of reality, and you'll be all good. So the problem with eventual consistency is, depending on your use case, this might not be good enough. If you need actual real-time access to consistent values, this isn't necessarily good enough. It also kind of requires for you to solve a lot of problems that are off the critical path. So at the very least, it moves some of these problems to the background, but you still have to figure out a way to resolve conflicts. So when you have writes that are concurrent, or if you have, say, insert operation that comes, or a delete operation, and then another delete operation, and it depends on some data that you've deleted in the past, you're going to get inconsistent views of the world, and you need some way to reconcile that. So there's two ways that systems tend to deal with this. It's like some reconciliation system, or actually just doing rollbacks, saying like I hit a conflict, I'm not sure how to proceed, roll back to a known state and say that that's the state of the world. But that gets very complicated. How many people here have heard of Kyle Kingsbury, or Afer, as he goes by online? Awesome. Okay, actually about half. So Kyle Kingsbury is a guy who wrote a series of blog posts called the Jepsen tests, named after the Canadian pop singer Carly Rae Jepsen. So what the Jepsen tests do, in a nutshell, is run various distributed data stores that we use in production systems through a battery of tests that test their kind of guarantees about partition tolerance. So it takes something like Cassandra or Zookeeper or Kafka or RabbitMQ, all these different data stores and queue systems and whatnot, and forces a network partition while a series of writes is happening, and figures out, okay, so we've got a divergence of state in the system. When the network rejoins, what's going to actually happen? And oftentimes, what's said will probably happen isn't what actually happens, and he's pointing out, inconsistencies in some of these implementations, which is natural, because if you look at eventual consistency models, there's not a lot of clarity on how to write a reliably, provably correct consistency model, eventually consistent model. So the Jepsen tests kind of just pointed this out, and this is the reason I find CRDTs interesting, because CRDTs are an attempt to provide some theoretical backing for a tool set that we can use to provide what I'll go into, which is called strong eventual consistency in a distributed system. So this is why CRDTs claim to be a big win. Now, before I go into too much detail about CRDTs, one thing that's really important to, took me a while to grok about them, is that CRDTs aren't like an invented technology. This is something that was more observed. It's a set of characteristics that were observed about certain types of data and certain properties about data types, that if a data type can satisfy these properties, interesting things tend to happen. And they're a way to implement what's called strong eventual consistency. So strong eventual consistency being a subset of eventual consistency. The idea behind strong eventual consistency is that you'll still have divergence in a system, but if you have a series of updates, you should be able to apply those updates to a local replica in any order and with duplicates, and you'll still end up with the same state. So you don't need any kind of central consensus system to coordinate updates in your distributed system. Does that make sense? I'm seeing some nodding heads. Cool. So one example, like the easiest way to explain strong eventual consistency is in the example we saw before, where you have a conflict, you have concurrent updates to some value in a system. One way to resolve this is just to say, if I see a conflict, I'm going to throw it away. So when it comes time to do a resolve, or when it comes time to try to get all of the nodes in a system to agree on a state of reality, whatever one I see last is the one that wins. So that's called a last writer wins element set. And that's a way of saying okay, there are no conflicts, because when I encounter a conflict, I just throw something away. That's as long as every node agrees that that's what happens, then that can be an acceptable way to do this, and to say every update is immediately durable. But I'm going to walk through, so the paper walks through a trivial CRDT to explain these properties. And if you think about a set, just a simple set as we know it, and it's got one operation only, which is an add element set. So this is the data type, and this is the only thing that we can do to a data type, is we can add an element to it. The add element operation commutes, right? So I can say if I have A, which is a set ABC, and if I have B, which is a set with a single element D, the union of those elements is commutative, right? Because A union B is the same as B union A. It's also associative. So if I have another set in there that I want to, add a set with a single element, and I want to add that element to set A, I can do the union of B and C together with A is the same as the union of A and B union with C, right? So it's associative as well. And it's idempotent. So I can implement, I can say, do this operation, add an element to the set, and then the resultant set, add another element to it, add the same element to it. The result is going to be the same, right? So I can repeat the operation without affecting the global state. So what's interesting here is in this example, I actually have enough to solve some real world problems. I mean, mind you, they're not really interesting problems, but I can solve, say, I can do like a mailbox or something like that. Something where things come in and that's it. I can represent that as a simple CRDT. If I wanted to add a delete operation, I could do that by, and this is very common in CRDTs, I can do that by having a delete set. So an add set and a delete set together make a logical mailbox with the add and a delete operation. And there's a number of different known CRDTs like this. So, when we define CRDTs like that as a set whose operations are commutative, associative, and idempotent, then you can start to think like, well, there's a number of things that we know satisfy that criteria. So there's different things like state-based increment-only counter, which actually we could represent as the number of elements in a set, for instance. There's a last writer wins element set, which actually I'll go into in a little bit of detail. But these are all examples of things that, of data types where we've observed that they have these characteristics. So we could actually build systems that use this, that are, that guarantee strong eventual consistency and kind of get around the cap problem. Now the problem with this is pretty obvious if you think about it. If you have, an add set and a delete set to do something like a mailbox, then you're going to have two sets that grow without bound, right? So that's not a very practical solution at any kind of scale. So the authors of the paper were like, okay, well that's a good example of the theory of what a CRDT is, but let's try something that's non-trivial. And like I said, the paper is very exploratory about this, so it's trying to figure out, can we use this observation in a kind of real world scenario, solving a difficult distributed systems problem at some kind of scale. So they implement a CRDT called TreeDoc, and the use case behind this is to implement a collaborative document editing system. So you think about like Google Docs or any of the collaborative code editors or that you use in interviews or anything like this, where you can have any number of participants contributing to some data set being the document, performing operations, and you need some way to represent that and that's scalable. So TreeDoc is a CRDT that implements an ordered set with insert, at, position, and delete operations. So we have two operations on this ordered set, insert, and it takes an ID, and an atom. So you can think of atoms as just some piece of data that we're performing some operation on. And atoms are represented by an ID, which I'll go into the criteria for. And that's all it does, okay? So before we can really go into the example, let's talk about the model that they were looking at implementing this in terms of. So the model is a distributed system. It supports what's referred to in a lot of papers as epidemic communication protocol. An example of this is like gossip protocol, used by a lot of real world systems. Is that, are gossip protocols unfamiliar? I'm getting some nodding heads. So basically a gossip protocol, like the word suggests, you can think about it as, a node in a system will tell another node in the system about some operation. It'll tell another node in the system. It'll tell another node in the system. There's some formalization behind this, but it's a way of guaranteeing that eventually some piece of information will propagate throughout the whole system. And it's a peer-to-peer kind of multi-broadcast type system. So the model that we're going to base TreeDoc on uses something like the gossip protocol, and it supports a multi-primary execution model. So like I was showing in the earlier examples, systems like MySQL, PostgreSQL, and their default configurations, if you have secondaries, you usually support a single primary kind of setup. This is not that. This is a setup where you can send reads and writes to any node in the system, and it shouldn't matter. which is important for availability. So a random site will, in this setup, a random site, we're going to refer to nodes in the system as sites. The paper uses that terminology. In this setup, a random node in the system will receive an operation. And so in this case, it's the update operation x is equal to 8. It'll initiate and execute it against its local replica. Okay? So the site has a local copy of the data. It accepts this operation and it updates its local replica. And then it will do a broadcast to say x equals 8, and another site will initiate that update against its local replica. And eventually you get some kind of convergence, okay? So this is the computational model that you can think of TreeDoc running in. And it's funny reading papers like this for me, because I'm not an academic. I read papers like this and there's a lot of hand-wavy details, and I'm like, wait, gossip protocol implementations are really hard actually, but apparently not. So just pretend that this all works and everything will be fine, right? So let's look at how they actually structure the CRDT. And we're going to look at this, and then we're going to look at how it satisfies some of the conditions that they talked about. Like I mentioned, this is an exploratory paper, so you're also going to run into some uh-oh moments where, like often happens, you have some theoretical principle, you implement it in reality, and you start to see where some of the edge conditions come up. But we'll see that they did some interesting work on this. And like I mentioned, this paper was written in 2009. A lot of work has been done by actually the same authors in some cases, where they've taken those edge cases and figured out better solutions to them. And I'll go through some, at the end of the talk, some real world examples where people are actually solving these problems without running into some of the edge cases by accepting certain trade-offs and whatnot. But let's look at the TreeDoc CRDT. So like I mentioned, this is a CRDT that implements an ordered set with insert at position and delete operations. So just to review, you've got an insert function. It takes an ID that's going to identify this atom and the new atom to insert into the document. And then you've got delete, and you can give it the ID, it will get rid of that atom from the document. Identifiers have some certain properties that they have to meet. So 2 replicas of the same atom, remember that's a piece of data that we're making a change to, have to have the same identifier, okay? So identifiers are global to the system. No 2 atoms can have the same identifier. So an identifier in the whole system uniquely identifies one atom, one ID. No atom's identifier remains constant for the entire lifetime, an atom's identifier remains constant for the entire lifetime of the ordered set. So IDs don't change. And there's a total ordering of IDs. So you can look at creating one atom, it's got ID 1, let's say. You create another atom, it'll have an ID that's greater than 1. You create another atom after that, it'll have an ID that is greater than that, and so on and so on. So there's a total ordering in the system. And we have to also assume that the identifier space is dense. So given 2 IDs, P and F, for instance, we can allocate an identifier that exists between those 2 values in the total ordering, okay? And there's an interesting observation here, which is that the set of real numbers is naturally dense, right? But you can't use the set of real numbers because if you were to constantly increase the precision required to represent that identifier, it grows without bound. So you're going to run into a scalability constraint, a theoretical constraint. Does that make sense, the total ordering? Okay. So TreeDoc is a tree. And what we can see is an atom identifier, which we're going to refer to, the paper starts referring to as a TID, represents a path in the tree, okay? So in this case, the atom C, which is just a character that someone typed in a collaborative document editor, you can imagine, it's got the identifier empty string, okay? The atom B has the identifier empty string 0. In this case, A has the identifier empty string 0, 0. Right? So again, there's a total ordering to these identifiers, and they identify an atom uniquely. And remember also, this has to be globally represented throughout the system. Food is coming, don't worry. I saw James run off and I was like, pizza. All right. So because different sites might allocate the same TID, different sites in this case meaning different clients, we run into our first problem. So we said that IDs have to be globally unique in the system, but you've got two disconnected sites, meaning let's say my computer and Manu, your computer, are initiating an update, and we could possibly, because we have no kind of consensus protocol or we're not necessarily directly connected, we're not going to be able to figure out that we both have unique IDs. So what we do is we use a site ID, okay? And in the tree structure, we can represent this by having major nodes and mini nodes. Mini nodes are distinguished by the site ID disambiguator. Okay, so inside a major node, we have mini nodes that are, the atom and the TID, but then they've also got the site disambiguator, which is included in that TID. Does that make sense? I know it's a bit to follow. So what ends up happening is, a site initiates some kind of update operation, and that site identifier is included in the identifier, which means that they are satisfying that property, that they're globally unique in the system. So in this example, DA, for instance, over here, is the disambiguator, and this site, identified by this disambiguator, initiated an insert operation with the ID blank string 00 and the value A, right? So you can see how even though the origin of the updates are coming from totally disconnected states, they're still maintaining the properties of identifiers. So let's look at just a few sample operations. I mentioned that there's insert and there's delete, and insert takes an ID so it can insert into a position, and delete just takes an ID. So in this case, we're going to delete 00. What node in the system does 00 identify? A, that's correct. So what we do is we actually don't delete it, we mark it as a tombstone, okay? So we say, okay, A is taken out. Because remember, this is represented as a set, and that set doesn't have a delete operation on the set. The delete operation just marks it as a tombstone. So site F initiates an insert 111G. Okay, so 111 is the ID, and G is the atom. Where's this going to fall? Who said that? Yeah, right here. So what we can see is it appends it to the rightmost side of the tree, okay? Now, there's already a problem that we can start to identify. Remember when we were talking about the trivial CRDT, one of the problems was that it grows without bound, right? We've got a similar problem here where if you let this go on for too long, you're gonna end up with two situations that are not exactly ideal for scalability, because there's gonna be storage and performance implications here. You're gonna end up with a tree that grows without bound, meaning it's just riddled with tombstones, but you haven't actually deleted any data. And you're also gonna have a tree that's badly unbalanced. So you can't guarantee that people are gonna be inserting into the tree evenly, so you're gonna end up with some crazy structure that has, like I said, storage and performance implications. So this is where, the first kind of uh-oh moment, they introduce a new operation called flatten. And what flatten does is it turns the tree into a flat array, okay? And you can represent a flat array as a balanced tree, so there's no need for an inverse operation, but it basically takes this big tree structure and it just says, okay, flatten it, store it as a flat array, everything's fine, you can now store it efficiently, etc. Now the problem here is, you can see in the example where we were looking at the actual structure, the TIDs actually identify their position in the tree. So flattening it naturally violates one of the properties for identifiers that we mentioned earlier, where it's going to require changing TIDs. So I love the way that the authors of the paper deal with this. They're just kind of like, oh yeah, so we don't do that anymore. We just, that's changed. It's almost like stream of thought, So the other problem is that a flatten operation on a tree structure doesn't commute with other update operations. So if a flatten and update happen concurrently, they don't satisfy those observations, those properties that we made earlier about idempotency, associativity, and commutativity. So that's a problem, because then you'd need some kind of consensus or something. So, that's a big problem as well. So the way that they deal with this is, I was mentioning earlier, one way to implement strong eventual consistency type models is to say everybody just agrees what happens when a conflict comes up. So in this case, update just wins. So if you have a flatten and an update operation that happen at the same time, or flatten and insert, sorry, then the flatten aborts. Whatever site tried to initiate the flatten just doesn't do it. Now the tricky part about this is that you need some kind of, they recommend two-phase commit or Paxos commit. You need something where, this operation is unlike the other operations that we're doing. You have to say, initiate the operation at some site, so the client says, or some site says flatten, our tree is growing too large, or we're just doing this at a regular interval, let's initiate a flatten operation. It has to then ask every other node in the system, are we currently doing an update? Meaning, if we're currently doing an update at any part of our system, because remember this is a multi-primary system with a broadcast model, we have to abort the flatten because those two operations won't commute. So in this case, if any site votes no, or if a site has crashed, meaning there's no response from that site, we just stop the flatten operation because it's not going to work. So this is really like a GC implementation. Flatten is taking a large unwieldy data type and condensing it down. And we also have this problem of all these tombstones. So you can get rid of all these tombstones. You can represent the tree as a nice balanced, efficiently storable data structure. But GC requires some form of consensus, right? Because you need to get every node in the system to agree on this, and this isn't a CRDT. So in order to have them converge on a state, you need some kind of consensus. So, like I said, this is an exploratory paper. This is one of the major uh-ohs, but what they did notice, and this is notable, is that the garbage collection cycle can happen off the critical path of a request, right? So it's better than some setups because you're not going to be blocked waiting for some kind of GC cycle to finish, and you're not going to be blocked by any kind of consensus protocol while it's going on. You're going to be able to, as a client of the system, just go forward and assume your update was working or your read worked. So the other thing to think about is, a lot of what we've talked about so far kind of assumes a static configuration of the members of this cluster. One of the difficulties here, if you think about the use case again, they're talking about online document collaboration. So imagine a bunch of people, I don't know, what's something that a lot of people would collaborate on? Writing some fan fiction for their favorite sitcom or something like that and commenting on things as people are writing it. I have no idea. But you can imagine in this situation, you're going to have sites, meaning you as the user who's going to visit this website or whatever the system is represented as, and you're going to enter, you're going to do some work, and then you're going to leave. You can't all of a sudden participate in consensus. You can't do any of this stuff. Also, in a real-world setup where you have machines in a networked data center and they're part of a cluster, you have to assume that machines are going to die, switches are going to fail, things are going to happen. So you're going to have large numbers of dynamic participants in this system, and that presents some problems. So I liked the way that they solved this. This is another kind of uh-oh, but what they do is they say there's now two types of sites in this system. What's up? Is pizza here? Oh, okay, cool. This is actually a good break point, so thank you, Alexi. Let's break for pizza, and then we'll all be much fuller. The complicated part of the talk. All right, so I'm still back up. Okay, good. Slides are working. All right, so where we left off, somebody, while we were eating pizza, asked me a really good question, which was that you're going to have this situation where if you have sites that require consensus, then you have sites that are coming and going. You're not going to be able to really participate in any meaningful consensus because consensus requires that you have well-connected, well-known set of hosts that are going to participate in that. And that's one of the reasons why it's a bottleneck, one of the reasons why it's hard to scale, et cetera. So in this system, you run into some problems. What they choose to do is to divide sites into two subsets. And one of the subsets is referred to as core sites. And core sites participate in things like consensus. The The other site is referred to as the nebula. The nebula do not. So the other thing is core sites participate in flatten operations. The nebula do not, okay? At least not in the same way. So stay with me, I'll try to get through this part. If we refer to, so the problem with flattens is we saw flatten operations change the structure of the tree. They change TIDs that identify atoms. Okay, and we said earlier TIDs can't change. Now they have to because we have to perform these flatten operations every once in a while. So what we're going to do is describe the period between two flatten operations as an epoch. Okay, and sites can be in different epochs. Core sites, however, are all in the same epoch. Right, so they all participate in a flatten operation together. Like we said, core can actually be as small as one node, which is interesting. I haven't actually mapped it all out or drawn it all out, but you can have a small enough core set that contains just one site. But they'll be, so you do a flatten operation, and all of a sudden TIDs that identify atoms in one epoch are no longer applicable to TIDs. They can't be compared or used in another epoch. So what ends up happening is, they're invalid from one another. You can't talk about the same thing using this same identifier. So we've now introduced another violation of the properties of identifiers that we mentioned earlier, which is that they all refer to the same thing. The way we get around that is epochs. Basically, the way I was trying to think about it when I was trying to understand this is epochs namespace identifiers. You could kind of think of it that way. So what this means is that you're going to have drift in divergence. You're going to have sites in the nebula have an outdated view of what's going on. They have TIDs that are not correspondable to the TIDs that sites in the core set of sites have. So periodically, any site in core will initiate what's called a nebula catch-up protocol. Okay, so it's basically instructing all of the sites that are not in the core set, you need to update to the current epoch. You need to get with reality. Okay? So in this example, I'm just going to try to visualize this a little bit. You've got a bunch of sites in core, and they're all in epoch n. And you have a bunch of sites in nebula. They have epoch n-1. Okay, so in this case, to sort of simplify, we're going to assume that one flatten operation has happened, right? So that means we're one epoch apart. So one flatten operation has happened. The nebula sites don't know about that flatten operation. The core sites do. So they've still got TIDs that don't mean anything in each other's context. So a core site initiates a catch-up protocol. And what ends up happening is, in this model, each core site maintains a buffer of updates. Some in the current epoch, n, and some in the old epoch. Okay, so as it was receiving, these are updates that happened before the flatten operation, these are updates that happen after the flatten operation. And because it's a core site, it participated in a flatten operation, it did a GC cycle on its TreeDoc, it knows which is which, right? It kept the buffer. Now, the thing is, it's going to send these updates eventually to sites in the nebula. That's the idea. And the nebula is woefully, ignorant of the current epoch. Doesn't know that a flatten operation happened. So it's got some epoch identifier. In this case, we know it's n-1, but it doesn't necessarily know that. And it's got a buffered set of operations that it's going to send to core. Okay. So core site initiates the catch-up protocol, and what it does first is it sends the nebula sites the updates in the old epoch. So it knows that, hey, you can understand these TIDs. I remember when I was like you, and these TIDs meant something. They mean something to you now. So the nebula will then initiate those updates on its local replica, and then initiate a flatten operation on its local replica. Okay. What it needs to do during this flatten operation, though, is it needs to keep a mapping of old TIDs to new TIDs. Okay? So the TIDs that refer to those atoms before the flatten operation and after the flatten operation. It translates the TIDs in its buffered messages into TIDs in the new epoch. And the way it does that, so the paper actually describes a identifier translation algorithm that I'm not going to go into because frankly it's a lot to cover in a slide presentation and it's not particularly interesting in the context of CRDTs. So for those who haven't read the paper, there's a whole section on the TID translation algorithm. I'm going to hand wave and just say pretend that there's a really efficient way of identifying or translating TIDs in an old epoch to TIDs in a new epoch. So once it's done that, it can then send its updates to core, right? Because it's flattened, it's brought its TIDs up to date. It now has the same kind of view of the world that core does. It can send its updates to core. Core now participates in the same state of the world that it does. They're converged for the most part, and at this point, because Nebula is all grown up, it has a current state of the world, it can actually decide whether or not it wants to join the core set, become a well-connected site. And there's a consensus algorithm. They mention that you need some form of consensus, or I think it's actually that they mention, the authors mention that core sites participate in like some kind of membership election, and they say like, do we want you as a member of the core? But the point is, at this point, the Nebula site is caught up. It can choose to join the core or remain part of the Nebula. That's the Nebula catch-up protocol. See what I mean is like it's about implementing a CRDT that's non-trivial. It's really non-trivial. And every once in a while running into these situations where there's an observation made, we have to come up with a solution to the observation. And in a lot of these cases, the observation, for me at least, were dense. They were definitely, the solutions to the observations made were really complicated. And Nebula catch-up protocol was an example of that. At least complicated for me. Much smarter people, they just see this and they read it and they get it, I'm sure. So the authors actually described that they implemented this TreeDoc, and they ran a few experiments to test their hypotheses. Remember, one of the main reasons for doing this was to try to come up with a solution that solved the use case, which was collaborative documented editing, in a really performant way that was easy to scale. So what's really neat is they actually ran TreeDoc on Wikipedia articles and Subversion code repositories. And they took the LaTeX, the typesetting language, they took the Subversion repository and looked at all the changes, and basically those were all atoms, or changes to atoms. And in some cases, atoms were single characters, in some cases, atoms were paragraphs. They also ran it against a bunch of Wikipedia articles. I love the fact that the George W. Bush article in Wikipedia was a particularly interesting one because it resulted in a ton of updates because of vandalism. So people didn't like George W. Bush, they would update the Wikipedia page, someone else would go, no, take it out, and it just ended up with all these. So in that case, it actually ran into, it resulted in a TreeDoc structure that had 95% tombstones in the absence of flattening. So it really reinforced the need for this GC cycle, because that's a very inefficient data structure, right? With periodic flattening, though, the slowest update, I think this was to the Wikipedia George Bush article, the slowest update took 0.3 milliseconds. So that's the worst case. That's pretty good. So the conclusions, that I had, this isn't the actual conclusions of the paper. They go into much more detail about much more, heady stuff. But for me, it was pretty evident that when implemented, this was performant, pretty easy to scale. Depends on consensus for GC and for things like core membership, but they're all off the critical path. So that's better than the situation where you're waiting, or a request is waiting for some kind of consensus to happen before it can return a result. In this case, you can continue to do request response, cycles, and GC and other things are happening in the background, but they're asynchronous. They're not going to block you. And the metadata of the tree, this was interesting. Like it encodes in the actual structure of the tree a causal ordering of updates, right? Because the TID identifies where in the tree an atom exists. The site and disambiguator being part of that TID, you can derive a causal ordering. This update caused this update. This this delete happened on this set of changes. So that's TreeDoc. That's the paper. What I want to do now is just spend some time looking at some real-world examples of CRDTs. I'm going to focus on one in particular, just because I'm more familiar with it, and we'll go from there and have some discussions. So ever since, like I mentioned, this paper was 2009. A lot of work has been done since then. React has now gotten support for CRDTs. There's a number of different data types that are stored using CRDTs in React now. So flags, registers, counters, sets, and maps are supported as of 2.02. I'm pretty sure there's earlier versions that support this. I just grabbed the first link I saw. There's also really interesting, so this predated the React stuff, but SoundCloud, does anyone know the streaming, like the music service SoundCloud? Anyone not know it? Basically think about it as you're able to upload sounds, share them with people. A lot of artists use it to like promote their music and stuff like that. They implemented a CRDT-based system for their activity feed. So in a social network, when you follow people, let's say all of you are SoundCloud users and I follow you all, you can think of like Twitter as like this. I follow you all and you do updates and I get those updates in a feed. It's a time-stamped series of events, right? So Jesse updated something, and then Manu updated something, and Donnie updated something, and I see that in the ordering. So what they decided to do to improve their activity feed system was they decided to implement it in terms of a last writer wins element set CRDT with inline garbage collection. If that doesn't mean anything, don't worry. We'll go through it. So this was designed for a fan-in on read model of activity streams. Okay. So let's look at dissecting what they said there. Last writer wins element set. I'll explain what that is, but the idea is it's got these three operations. Insert, you give it a key, a timestamp, and a value. You can delete a key and a timestamp and a value. You can select a key, an offset, and a limit, and get a bunch of things back. Something interesting to note here, which is that this is where TreeDoc had all of these complicated problems that they needed to solve. This is where Roshi, this system that implements SoundCloud's activity stream, actually does a service here. It says we're depending on externally generated timestamps to represent the ordering of updates, and that's fine. So based on those timestamps that are externally generated, so they're generated by sites in the system, they're not generated by one central place. We're going to just say, in the case of conflicts or whatever, last writer wins. So that's an easy way to deal with it. And we'll see it becomes really simple. So most CRDTs are sets are represented as an add set and a delete set if you want to support those operations. What you have here is an add set, S plus, a delete set, S minus, and then the actual logical set is the presence in the add set minus the presence in the delete set is the logical set. Makes sense? So you have updates, deletes, and you can construct a view of the world from that. So, and these are ordered by timestamps, some kind of counter. Technically, it could just be any kind of increasing counter. So concretely, and this is all, by the way, taken directly from a guy who works at SoundCloud. I'll give the link to his presentation on how they implemented this stuff. But I'm just going to take his example, walk through it, and then we'll apply what we hopefully learned about CRDTs to this. So in this example, we're using S is the name of the set, and S is a user's outbox in an activity feed. So SoundCloud being a music service, they got Snoop Dogg. He's got an outbox of updates that his followers will receive. A, B, C, D is some kind of activity that is being notified to his users. So in this case, Snoop Dogg reposted The Economist. They published something, sure, he reposted that. And then 1, 2, and 3, and 4, and whatnot in this system are timestamps, okay? But like I mentioned, that's actually an unimportant detail. They could just be any kind of increasing counter. So let's look at what operations would do. So we have insert into the set, because we mentioned the API looks like that. So in this case, the set is the key, or the key is the set, rather. So we have insert D with a timestamp of 5, okay? So what's this gonna do? It's gonna add it to the add set, and then it's gonna become a part of the logical set. And what we're also gonna be able to do, because we have a timer value, a counter that's higher than the version in the delete set, we can go through and garbage collect this, and there we go. So that's now the logical set. So we just performed an insert operation, okay? That makes sense to people? I'm seeing more nodding heads, good. All right, so what happens if we want to delete D and we give it a counter value of 4? Can anyone guess what this is going to do? It's going to do nothing in this case, because we already have a value D in the add set, but it's got a greater counter. Okay, so in a timestamp scenario, or actually in any scenario, this would be assumed to be an operation that happened in the past. So because this is a last writer wins element set, we're just going to discard this operation, nothing happens. So now we want to add C to the delete set. So we want to delete C, and we give it a timer of 4. We can see that we have C already in the add set with a timer of 3. 4 is greater than 3, we're all good to go. So we can delete that, and we remove it, okay? We deleted C, we want to delete C again, but what's going to happen now? So we have a counter of 4. In this case, it could be, whatever. It's a no op, okay? So the neat thing here is that set, a Roshi set, which follows those rules based on those operations, is a CRDT based on our original observations. Operations on it commute, they're associative, they are idempotent. And what's neat about this is you can imagine all of those operations happening in a network scenario where, like we mentioned, nothing is really reliable. You can have messages repeated, you can have messages dropped, you can have messages arrive out of order. It doesn't actually matter. Each node in a system, or each site in a system, can receive the set of updates in any ordering, and there can be duplicates, but they'll still converge on the same eventual state. So this is a really good example of strong eventual consistency. And as we can see in this case, because they depend on the one trade-off, that they depend on an external counter, timestamps generated on sites, it becomes radically simpler than looking at something like TreeDoc. Do you all agree? This is a much simpler set to kind of work with. But it's because it has that trade-off. So this wouldn't be very good for an academic paper, but it's very good for a real-world setting that takes lessons from this academic paper and says, okay, well, there's a lot of complicated scenarios we have to deal with in theory. Let's just say, you know what, if we accept the fact that timestamps may drift, but what's the worst that can happen? We get updates out of order in the activity feed or something like that, that's fine. It becomes really, really simple. And this will scale without any kind of consensus system. You can have temporary divergence, and then eventually things will converge on a state of reality. So some quick resources. I linked to the paper in the beginning, and I'll make sure that the slides are shared somehow. There's a great talk given by Marc Shapiro, who's the primary author of the paper, that happens many years after, well, not many years, especially in academia, we're talking like 3 years. But he gave a talk called Strong Eventual Consistency and Conflict-Free Replicated Data Types. It goes into a lot more detail and brings up to date some of the research done in this area. The presentation that I stole all those Roshi examples from on CRDTs in production at SoundCloud is on InfoQ's website. And comprehensive study of convergent and commutative replicated data types is a paper that was published by some of the same authors of the paper I've just presented, but was done in 2011, brings up to date some of the current work done on this area. Okay? I know we had some questions during the lunch break, but any questions? Yep.
During the TreeDoc example, when a flatten comes in and you try to get the consensus amongst all the nodes, and every node has to say yes or no.
Yeah.
What happens if a node says yes and then it receives an insert or update like operation?
So that's a good question. Just to repeat for the video and for other people, what he was asking is if a flatten operation is happening, and while that flatten operation is happening, an update happens, right? So the conditions for a flatten were met because no update was happening at the time that the flatten was initiated, but then during the flatten operation, an update happens. And that's where the Nebula and core epochs come in. So an epoch is an identifier that identifies the space between two flatten operations. So that update that came in after a flatten was initiated would end up in the old epoch. And core sites, which initiate flatten operations, maintain buffers of updates in the old epoch and in the new epoch, and eventually send those out to Nebula sites, and they do their catch-up protocol. So you would have a convergence in that situation. But that's what necessitates the buffer of update messages in the old epoch and the new. So as soon as a way to think about that is as soon as a flatten operation happens, you're going to have two sets of updates that you have to maintain. Once you kind of reconcile all that, then you're going to flush your updates in the old epoch to all the Nebula sites. They're going to do the catch up, and then you're going to have one buffer of operations again, and then a flatten will happen, and that operation is the old epoch now, and you have two sets of operations that you're buffering. Any other questions?
So the last real case scenario, I'm thinking that it's more like who is following, who is adding a follower and taking a follower away. What if this case, like just as you said, a flickering? Let's say if the core, a lot of people are updating their visiting counts. How would that? How can we deal with that? I mean, it's a set. It's not a set anymore. It's just increase the visited number.
Oh, you're talking about an example we were discussing over the food break. And yeah, what we were talking about is another kind of value that you might store as a CRDT, which would be like an increment-only counter. So in an example, I think I gave an example where Flickr or something has like view counts for photos. You know, hypothetically, you could store that value as a CRDT probably. And in that case, it wouldn't look like a Roshi set. It would look like an increment-only element set or an add-only element set. And what you're doing is the count would be, you know, the size of the set, for instance. So you don't actually have delete operations because it is impossible to unview something. And there's probably another way that you could kind of bend that problem, because what you'll run into, you know, first there is a counter in that situation. And this is actually like, this is formalized. I'm not well versed enough to explain the formalized, but I'm just riffing. If you have like a set that the size of the set is a counter value, then you're going to grow without bound. So you need some kind of GC, just like Roshi does in its case, and you could easily like just replace the value with an integer at some point, held like in some other value, and then empty the set and restart it, and it's the addition of that integer value and that set size, something like that. Peter?
When you were talking about Roshi, you were talking about an externally derived clock of some sort.
Yeah.
In practice, is that usually like NTP or a vector clock or something?
I think theoretically it can be anything. I think in their case, I think I remember the author of Roshi, Peter, when he gave his presentation at QCon, he talked about it was NTP at that setting. He gave a funny little hand wave. He's like, we're a website, But the idea is that it wasn't that big of a problem in practice. The worst case scenario was acceptable, and the model allows for something that's much more, fault tolerant, like a vector clock or something like that. Cool. All right, well, thank you very much.